Okay, so we're going to move on now to look at transformers. So 11Y1, we've already covered this. 11X1, this isn't something we got to before. So we're going to take a look at what a transformer is, what it's used for, particularly why it's useful with distributing electricity via the national grid. And there's a couple of key equations that we're going to come across, practice using. Okay, so you might remember in year 10 we talked about transformers a little bit as part of the process of distributing electricity, but we didn't go into a lot of detail about what they actually do and why they're useful. And this is really the payoff for that. We come back and we talk about that now. So first of all, let's talk about what a transformer is. Okay, basic idea of a transformer is very, very simple. We've got an iron core. It's often called soft iron, and I don't literally mean it's soft by that. What they mean by that is that it's easy to magnetize and demagnetize. So there's an iron core, and then there are two entirely separate coils of wire wrapped around it. So on this side we've got the primary coil, and on this side we've got the secondary coil. Okay, when the transformer is being used, we're going to connect an alternating current up to the primary coil, and that's like the input to the transformer, and over here we're going to get an output. Okay, now we need to explain what's going on there and why. Okay, so the alternating current in this coil creates a magnetic field in the iron core. Okay, now if this was a direct current, it'd be staying the same size and the same direction all the time, and we get a steady magnetic field in the iron core. But that's not what's happening. What we've got here is an alternating current, which means that it's changing size and direction all the time, which means that the size and the direction of the magnetic field in the iron core is also going to be changing size and direction all of the time. Okay, and that changing magnetic field in the iron core, what that does in the secondary coil is that induces a potential difference. And again, if we've got a complete circuit, that will make a current flow in that circuit, and it'll be an alternating current. Okay, so just take a minute there and pause and make sure you're happy with those three steps. The alternating current through the primary coil creates an alternating magnetic field in the iron core, which in turn induces an alternating potential difference in the secondary coil. Okay, now you can see in the diagram that there are different numbers of turns on the two coils. Okay, and that's a standard feature of a transformer. As we'll see, it'd be pretty pointless to have the same number of turns on both coils, so that doesn't ever happen. Okay, so either there's going to be less turns on the primary, like you can see here, or there'll be more turns on the primary. There'll always be a different number of turns on the two coils. So the number here, we use a capital N to number, and then we have a little p there to tell us it's a primary. Over here we've got the secondary coil, so that's capital N for the number and an S there, just so we know it's a secondary coil we're talking about. Okay, now what we're interested in investigating first of all is to have a look at how the output potential difference here, which we're going to call VS, V for potential difference or voltage, S so we know we're talking about secondary, how that compares to what we put in on the primary, VP. Okay, and what we'll see is that this depends fairly obviously on VP, but it also depends on the number of turns we've got on these two coils. Okay, so if we were all in the classroom, this is where I'd whip out some kit and we'd have a little demonstration and we'd take some readings and we'd look at what those readings would tell us. Unfortunately, we can't do any of that, so you've got to imagine here's our transformer. So you can see the top bit of the iron core there, and there's two bars that go up and down there, and these are my two coils. If you look closely, you can just about see there's 1200 turns on that coil and there's 600 turns on that coil. Okay, and we're just going to have a little look. So what we would do normally is we'd try some different numbers of turns on our two coils, and we keep the voltage or the potential difference on the primary coil at 2 volts all of the time. Okay, so to start off with, we'd have just to see what happens. We'd never do this in real life, but just to see what happens. Equal numbers of turns on the primary and the secondary. Okay, and when we did this, if we do this, let's see, there we go. What we'd find, if we had a really good transformer, we'd find that we got 2 volts there. Okay, so when there's equal numbers, there's 600 turns and 600 turns, we would get the same voltage on a secondary that we got on the primary. Okay, if we come down and look at our second row, we've got 300 and 600 on the secondary. Okay, so we'd still keep 2 volts on that, but what we might find this time is instead of getting 2 volts, sorry about my handwriting, we get 4 volts. Okay, third row, we've got 300 and 1200. Still 2 volts going in, but this time we might find that we get about 8 volts on the secondary coil. Okay, if you look now, rather than having more turns on the secondary, this time we've got more turns on the primary. So we've got 600 here and 300 there. If we keep 2 on the primary, what we'd find this time is that we might only get about 1 on the secondary. And here I've got 1200 on the primary, only 300 on the secondary, and this time you might guess by now I'm going to get about 0.5. Okay, now if we start looking at what all this is telling us, if we look up here, 600 to 600, if we compare 600 over 600, that's equal to 1. If we compare 2 over 2, 2 over 2 is also equal to 1. If we compare 300 to 600, that's a half. And 2 to 4, that's a half as well. If we look at 300 to 1200, that's a quarter. If we look at 2 to 8, that's also a quarter. If we look at 600 to 300, that's a ratio of 2. If we look at 2 to 1, that's a ratio of 2. If we look at 1200 to 300, that's a ratio of 4. If we look at 2 to 0.5, that's also 4. So what's going on here, hopefully now, is pretty evident. The ratio of the numbers of turns on the 2 coils tells us what the ratio of the 2 potential differences is going to be. Okay, so this gives us what's called the transformer equation. Okay, so for a perfect transformer, okay, a real transformer, there are going to be some energy losses, and this isn't going to be quite true, but for our purposes we can think of it as being a perfect transformer. There are no energy losses, and in which case this equation would be absolutely spot on. Okay, so the ratio of the 2 potential differences is always going to be the same as the ratio of the numbers of turns on the 2 coils. So VP, potential difference on the primary, divided by VS, potential difference on the secondary, will always be equal to the number of turns on the primary divided by the number of turns on the secondary. Okay, now this is an equation that's on the sheet you would get in your exam, so it doesn't matter if you can't quite remember it, as long as you know it exists and you know what to do with it. Alright, so what's coming up next is we're going to look at 2 different types of transformers. These are, or 2 different groups of transformers, I should say. Okay, if there's more turns on the primary than on the secondary, we would say we've got a step-up transformer. Okay, and I like to have a little think, what does that tell us about VS compared to VP? And similarly, if we have more turns on the primary than the secondary, we get what's called a step-down transformer. And again, have a little think, how would VS compare to VP? In fact, pause the video there for a little minute if you like, have a little think about that question, and then come back when you're ready. Okay, so what I hope you've realized is that if there's more turns, start this again, if there's more turns on the secondary than on the primary, then the voltage, the potential difference on the secondary is higher than on the primary. So the step-up transformer increases the size of the PD we get out of the transformer. Okay, whereas a step-down transformer, there's more turns on the primary, does the opposite job. This means that the output, the secondary potential difference is smaller than the input potential difference. So a step-down transformer decreases the potential difference. Okay, and all of the transformers that you'll ever meet will either be step-up or step-down, and we use them for different reasons, and we'll have a talk about those in probably the next video. Okay, so for the moment though, here's 3 questions for you to practice on. Okay, what I'd like to do is to just pause the video so you can see the questions, have a go at the questions on a piece of paper. Don't worry about making it neat. Use the equation that we've just been through, play back the video if you need any help, and have a go at these 3 questions. In a moment, when you're ready, unpause the video, and then we'll have a look at those 3 answers. Okay, so here's those answers. I'm going to stop this video here, and we'll take a look at some workings out if anybody's confused about how you got those answers. But I hope most of you have got those correct first time and probably won't need to look at the video of me doing the workings out. Okay.